Okay, and we will start from current slide. Well, actually, we won't start from current slide. I may even turn on the projector for you today. I just feel generous. So you'll be able to see what I'm talking about. Oh, before that, let me go over these announcements. I usually make the announcements beforehand. This one I should have. They do publish the menus for the week in the various cafeterias. I'm just going to make an assumption that y'all are here on Bessemer campus, so I'm going to read you these. Today is taco salad day, and I couldn't bring my lunch today, so I'm going to enjoy taco salad. Tomorrow is fish on the hot food line in short order on the grill, and Friday is short order only, okay? If you are on the Birmingham campus, either for lunch or the dinner, I do have the menus for those as well, so you're welcome to come take a look at that. I didn't need to put that one on Screencast-O-Matic, but it's there now. But I did want to put about the math team. Now, you met with Mr. Racy Friday. Did y'all decide on a day and time, Monday, Wednesday?
Monday, but
Monday.
I wasn't able to go to the first one. Those there called into work.
Okay. Okay, it'll be Mondays at 3? Okay. It's not going to be Fridays at 12 anymore. Mondays.
Both, though.
Oh, it's going to be both.
Yes,
so if you can go either one, Mondays at 3 or Fridays at 12. Okay? Now, this Friday we have a meeting at 1, so I know it won't be going past 1. So, and if you want to meet any on this campus, I'll be glad to do it. It's fun to do. I'll be glad to do that with you as well. All right, I've marked everyone here who is here. So we're going to continue in Chapter 1, Limits and the Properties. But before we do that, let me finish. Was that enough, or you want a little bit more on logs? Okay, all right. The question was a refresher on logs. And I started it with discussion about exponential functions. Give me your favorite base. Any number. 6. Okay. So let's say that y is equal to 6 to the x power. That's an exponential function. Okay. An equivalent exponential function an equivalent log function for that or equation says the same thing. Okay. That would be whatever is your input variable here becomes your output variable now. X is equal to, and then you do a log log, because this is not base E, base 6 of y. Okay? So the exponential function is that, the log function undoes it. Okay? Just to, I don't know if you think in terms of graphs, the exponential function would graph like this. Okay? By the way, just about always going through the point 0, 1. Because if you think about it, 6 to the 0th power is 1. So when x is 0, anything less than 0, a negative here, like -1, if x is -1, this would be y is equal to 1 over 6. So that's a fractional form. Okay? So it's going to be below 1, but always positive. Anything greater than 0, like x to the 1, that would be 6. So the next place would be up here. I don't have my graph drawn very well, but that would be the graph of the exponential function. Now let me draw the log function in a different color. You pick a color. Red? Okay. All right. Now, the log function reverses the x's and y's. Okay? So if you input a y now, you get out an x. Well, let's input this y, 1, okay? And what should be your output? Your x, 0, okay? Now, because this is approaching the x-axis asymptotically for negative x's, this approaches the y-axis asymptotically for negative y's, and then this also increases without bound. Now, kind of wish you hadn't done red, because I like to put, this is the identity function. y is equal to x, and all inverse functions reflect across there. And you can see the graph of exponential reflects across and becomes the graph of y. That's why we said the log of, you can only take logs of positive numbers. Log of 0 is not defined. Log of a negative number, never defined, ever, either one of those. Because the input here is all real numbers, its output is all positive numbers, not even 0, never reaches 0. So over here, the input is all positive numbers, never 0 or negative, but the output is all real numbers. It can be negative or positive. Okay? Now, that's the log function. The ln function would then be, you want a different color or go back to the original? Go back, okay, we'll go back to that. Now we'll do y is equal to e to the x, okay? Now, this is such a sort of famous function, even though e is just a number, it's an irrational number, but sometimes you'll see this as exp of x. I can't remember if calculators, some of the older calculators used to do that, okay? It's the exponential function. All it's doing is raising the natural base of our number system, e, to some power x, okay? Jeremy's here. Still all Y chromosomes, wow, okay. So, its graph, because e is less than, let me do this in a different color, pick one.
Green.
Huh? Green, okay, we'll do dark green. All right, and there's Elijah. We're not really doing anything out of the book now. This is just a review of logs right now. To plot this one, again, 0, 1 is a point, and because 2.7 is less than 6, it goes up a little bit more slowly than this, but crosses and does higher here. So the log function will then be like this. Let's see, am I doing it right? Yeah. And then, something like that, okay? And I probably should have done a different color there. Its inverse function would be x is equal to ln y. Okay. Now, so that's called natural log. The other is called base 6 log. LOG generally implies that you have a different base. But if you see an LOG with no base listed, most of the time that's base 10 because we got 10 fingers and toes, okay? That's how we learn to count, okay? But the natural base of our number system is that irrational number, E. And no, you're in here, you're hiding. There you go, Terrell. Okay. Still all Y chromosomes. Oh, wrong. Okay. So this is just a quick review of what a log function is. Any log function, you can never take the log of a negative number or even of 0. Okay? And they always look something like that. Notice there's no asymptote up there. It keeps climbing, like delta, but it never reaches an asymptote. It doesn't go up as fast as exponentials, but it does go up. Now, one of the big uses of logarithms in practical senses is when you're dealing with numbers that are astronomically large. For instance, does anyone know what pH is?
Acid or base level?
Yeah, it's acid or base level. And what you're measuring in pH is the hydrogen ion concentrations. The H stands for hydrogen. That's where it comes from. But with that, you're usually dealing with incredibly small numbers. 10 to the minus 7, 10 to the minus 12, 10 to the minus 5. Really, really small numbers. But you do a negate, okay, what it is the negative log of those numbers. So we usually talk then about if it's 10 to the negative 7, hydrogen ion concentration, that would be a pH of 7, which is exactly neutral. Any pH higher than that has higher concentration, more acid, but it has a lower pH number because 10 to the minus 4 is bigger than 10 to the minus 7. But that means you have more hydrogen ion concentration. So pH of 4 is very acidic. Okay? Probably like that Mountain Dew I just drank before I came to class. I didn't drink all of it, just a sip or two, just because I was feeling my throat was itchy. So that would be a very low pH. Soap would be maybe pH 10, 10 to the minus 10. Very low hydrogen ion concentration. You'd have more OHs in that. So that's an example of you take numbers that are really, really small, but you get it onto a scale basically never about 1 to 12 or 1 to 15, 14, something like that. That would be your pH levels. Decibels for hearing. Whisper like this. You can hear that. And you can go to a rock concert and hear that. Maybe head ringing afterwards. But you're covering a huge range of sound energy. Huge. So decibels takes a log of that sound energy, and then you're talking about decibel level, maybe 2 or 3 when I whisper, 12 or 15 for a rock concert or an airplane taking off, a jet airplane. All right, our first X chromosome. Good to see you, Nicole, right? Okay. Good deal. All right, we just had a little review of logs and connected them with exponentials and things like that. Is that a little better? Okay. Before it was just arm waving and talking. I thought the graph may help a little bit. All right, now let's clear this off the screen. Any other questions before we get started in the calculus today? This is part of calculus. A very important part. We're going to be talking about taking derivatives of exponentials, logs, and all sorts of things later. And you will learn to love the E function when you start doing derivatives and integration. It will become your favorite function in the world. I almost promise you. It's fine anyway. Okay. All right, we'll get there later. We'll see why it's the natural base of our number system. Never counted it that way until we got calculus, and then everybody got to loving it. All right, we were going to do example 10. This is the last example in 1.3, but 1.3 didn't have this in the slide set, so I went on and loaded 1.4, but I thought we'd do example 10 here. It says, find the limit of let me get my pen back. Okay. The limit of, as x approaches 0, of sine 4x over x. All right. We didn't do one exactly like that. We did one that looked almost like this, but not quite. Remember the one we know and love and did last time? What was it? That one. The limit as x approaches 0 of what? You got your book, flip back a page. Sine x over x. We know that one. Sine x over x, right? And what is that limit? 1. Now and always. Sine x over x is 1. As you do sine 4x over x, of course, if you plugged in x equals 0 there, you get 4 times 0 is 0, sine of 0 is 0, x equals 0 in the denominator, 0 over 0, indeterminate form. Can you say it's 1? No, it's not the same. So what can we do to that to make it look more like this? Second? Pull it out, okay, like a dentist pulls out a tooth, right? That would be very painful. Especially with no end. So let's not do that. We don't like pain. Yes?
Put it in front of the sign.
Do say it again.
Put it in front of the sign.
Aha! By it, you mean 4?
Yes.
Okay. I could do that too, but that won't quite be legal unless I do something else. Yes, if I put a 4 here and a 4 there, what's 4 over 4? And when can I do that? Anytime I want to. You can multiply by 1 anytime you want to. It doesn't change the value at all, right? Okay. Now, okay, what do we have? Well, it doesn't quite look like this, but let's just suppose, get used to this, we'll be doing this a bit. Let's give me another variable, any old variable, just not x. Y, okay, perfect choice, okay. Let y equal 4x. You okay with that? You all right with it? Okay. Then let's rewrite this. Limit as y approaches 0. What's happening to x if y is approaching 0? What's x approaching? Let's say it the other way. When x is approaching 0, what's y approaching? 4 times 0 is? 0. So it's still approaching 0. So I can write limit as y approaches 0 down here, right? And up here, the 4 is just 4. The sign is sign. And 4x is now at y over 4x is y. And look at that. I just have a constant times a function that I already know. That's the same as 4 times the limit as y approaches 0 of sine y over y. And guess what that is? Yes, that's 1. So this would be 4 times 1 equals 4. There it is. See how that worked? Shell game. No, I'm sorry. Trick. No, that's the method that we use. Okay? Get it to look like this. Get the same thing over itself. You do that by multiplying the numerator and denominator by 4. And then you have 4 times something that looks just like this. Only it's 4x rather than x. Then it's the same. So you have 4. All right. Let's see how the book did. Look at that. They got it right too. We're proud of them. All right. And this little technique of changing your variables is sometimes called substitution. Get used to it. We're going to be doing it not right away, but you will do it in time. All right. Any questions? No, I didn't. I didn't assign all the exercises in 1.3, so let me go over the rest of them. I'll just do all the ones I did before. Any of the odds 5 to 21, all those odds are in calcchat.com. 7 is in calcview.com. Any of either 23 or 25 or both of those are at calcchat.com. 25 is at calcview.com. Any of the odds 27 to 35, all those are at CalcChat. 29 is at CalcView. Either 37 or 39, both of them are at CalcChat. 39 is at CalcView. Any of the odds 41 to 45, all 3 of those are on CalcChat. 43 is at CalcView. Any of the odds 47 to 61, all those odds are at CalcChat. 53 is at CalcView. Any of the odds 63 to 73, all of them are at CalcChat. 65 is at CalcView. These are the ones more like the one I just did now. Okay? And they get a little hairier too. So play with them for a while. Sue, if you have questions, bring them to class. Okay? Any of the odds, any of the odds 75 to 81, all of those are on CalcChat. 75 is at CalcView. Any of the odds 83 to 89, all of them are at CalcChat. 83 is at CalcView. Do number 91, either 93 or 95, they're all at CalcChat, and none of them at CalcView. 97 is exploring concepts. Think through that one. You don't have to do anything unless you sometimes thinking involves writing, so you can write it down if you need to. 99 is a writing problem. You don't have to do that, but again, I'd like you to think through that. 101 is a physics application. Pretty good one to take a look at. And so are the rest of these. 103 is, so that's a good problem to look at. And then any of the odds, 105 is finding a function, okay? And then the rest of those 107 through 111 are proofs. I don't require you to do proofs, but especially if you're a math major or thinking about becoming a math major, you might want to start, training yourself and to look through and figure out how you go about doing proofs. They have some hints there and other things and some in the back, so you can take a look at that. I just don't think we have class time, especially since we lost a week or so at the beginning of the term, to do too much on that. Number 113 is to think about it. So you certainly you can read those and think about it. 115 through 119 are true false. You won't see true false on a test if I can help it. I hate those when I was taking classes, but they still are instructive to look at and figure out why it's true or why it's false. So I would definitely take a look at them. 121 is another proof, and 123 is a graphical reasoning. Again, those are things to look at, think through, but I wouldn't get too bogged down with it. All right, good deal. Any questions? 1.3. Okay, 1.5 is picking up with continuity and one-sided limits. Okay? Now, our objectives here are determine continuity at a point and continuity on an open interval. We'll determine one-sided limits and continuity on a closed interval. We'll use the properties of continuity, and we'll understand, it says you will, okay, and use the intermediate value theorem. Quite a helpful theorem there, okay? So, let's start with continuity. Probably haven't run into the word too much before, have you? Well, yes, you did, in a different form. When you talked about polynomial functions, what were two characteristics of a polynomial function? Smooth and continuous, exactly. Sine function, cosine function, smooth and continuous. Rational functions, most of the time smooth, but sometimes discontinuous if you have a vertical asymptote, right? Okay. Your other trig functions, tangent, smooth until you hit a vertical asymptote. Then it's discontinuous, okay? Secant, cosecant, cotangent, all are discontinuous at some points. So yeah, we've talked about continuity just as in the sense of, is it a continuous function or not? If it has a break, it's not continuous, okay? So we'll look at continuity at a point and on an open interval. Now, what do we mean by open intervals? Anyone remember that? Maybe a new term for you. An interval is something usually, yeah, what are you going to say? Okay, I think I know what you're talking about. That's continuity at a point, sort of, okay? But an open interval is usually your horizontal axis, is where you deal with intervals. Okay, an open interval would be some portion of that horizontal axis, but not necessarily counting the endpoints. That makes it an open interval. A closed interval would count the endpoints, but nothing outside, just things within. So when they say an open interval, that counts everything between 2 points, but not counting the endpoints. Okay, so just to get a little bit of definition there. So in mathematics, the term continuous has much the same meaning as it has in everyday usage. That is always true in science and math and everyday usage. Sometimes we get really sloppy with words in everyday usage. Math is usually pretty precise. Informally, to say a function is continuous at x equals c means there's no interruption of the graph of c. So if you think and picture the function like a polynomial function, no interruptions anywhere. They just go on forever. Sine functions, cosine functions, okay? But I think we did one in here where you had the little circle in there. That would be not a continuous function. And here's testing. All right. So it says a function is continuous at C means there is no interruption in the graph at alpha equals C. There's no hole there, there's no vertical asymptote there, there's nothing that breaks it. That is, the graph is unbroken at C, there's no holes, no jumps, no gaps. Okay? Now, even the absolute value function, it's not smooth, but it's continuous because there's no gaps, holes, or jumps anywhere. Something like this? Not. Okay. By the way, my arm waving doesn't show up on YouTube video. Okay. You're probably glad. Okay. Here is figure 1.6 in your text. Here it is on the slide. It identifies three values of x at which the graph of alpha is not continuous. At all other points on the interval a to b, what does that mean? Open interval, all the points in between A and B, but not counting A and not counting B, but everything in between. So here's A, here's B. We're not going to count this, so that open circle there doesn't bother us here. Okay? We're not going to count this. It's an open interval. That doesn't matter either. That one does not define x equals C because there's a gap there. There's an opening. Okay? Alpha C is not defined, so that's not a continuous function on A to B. Open interval A to B. This one isn't either. Okay? Again, the holes at the end don't matter because it's an open interval. It's just the points in between. But here you are defined at every point, but this definition and that definition are totally different. So this is not the limit doesn't exist at C. As you approach C on the x-axis in this way, your function approaches this value up here on the y, but if you approach C from the right-hand side, from the B side, then you're approaching a value down here. Those aren't the same. Limit doesn't exist, so this is not a continuous function either. Okay? Now this one, alpha is defined. See, this one, alpha isn't defined at C. Okay? Not defined at all. There's an open circle there, nothing. Here's an open circle on the graph, but it is defined at C. It's down here. Well, the limit as x approaches C is that value. The limit as x approaches C is the same. So it has a limit, but that limit is not the value. The value is down here. So that's not a continuous function. Three conditions exist for which the graph of alpha is not continuous. If a function is not defined somewhere, it's not continuous there. If it is defined, but the limit doesn't exist, it's not continuous. And if the limit does exist, but it's not the value at that, then that's also discontinuous. Even though it's defined everywhere, but the limit is not the same as the functional value. Okay. Blah, blah, blah. I mean, in real life, are you really going to hit those very often? Maybe occasionally, okay? But still, you have to get our definitions down and understood. So here are that figure appears that continuity can be destroyed, boy, that's pretty fierce, by any one of the following conditions. Number one, if the function is not defined at some value in that interval, open interval, then it can't be continuous there. If it's not defined, you can't tell what it is. Okay? The limit of alpha of x does not exist there. So the function is defined everywhere, but the limit at that point doesn't exist because they're going to different values. Or the limit does exist, and the function is defined, but the limit and the definition are not the same. It is not equal. The limit at x equals C is not the same as alpha C. That would be what the point is. So if none of those three conditions is true, then the function is called continuous at C, at any point C in the open interval. Okay? So here is your definition. Very important definition. Okay. Definition of continuity. Continuity at a point. A function f is continuous at C when these three conditions are met. Boy, do you think these are important? They've mentioned them three different ways. If alpha C is defined, okay, that has to be true. But all three of them has to be true. So f of c has to be defined, first thing to check. Number two, the limit as x approaches c of f of x exists, okay, and that the limit of f of x as x approaches c is f of c. Okay? Now, it seems like to me, if you just said that, you would have it done. Obviously, f of c is defined, or else you wouldn't say it if that wasn't, okay? And the limit does exist because you just said it exists in this. So it seems like to me this one wraps up the other two. But they always like to mention all three. A function is continuous on an open interval a to b when the function is continuous at each point on the interval. That means your c can go anywhere between a and b, and you always meet these three conditions, especially that. Okay? A function that is continuous on the entire real number line, negative infinity, positive infinity, is called everywhere continuous. Everywhere continuous. And by the way, remember your polynomial functions are everywhere continuous, your sine, cosine function are everywhere continuous, your exponential functions are everywhere continuous. Was the log function everywhere continuous? Can't take the log of a negative number. No. It's only continuous greater than 0. Okay? The tangent function everywhere continuous? No, because it adds vertical asymptote every half height. Okay, so, yeah. Is the absolute value function everywhere continuous? Yes. Not smooth, but continuous. Exactly. Okay, good deal. All right, let's consider an open interval I that contains this real number c, whatever it happens to be. If a function f is defined on I, that open interval, except possibly at c. Okay, so now we're saying it may not be defined at c, but everywhere else it is. And f is not continuous at c. Okay, then f is said to have a discontinuity at c because it's not continuous at c. Especially if it's not defined at c, it's discontinuous there. Discontinuities fall into two categories. Okay? You can either remove them or you can't remove them. Okay? Now, remember back when the function went like this, had the hole here and the value down here? Or just no value there at all? Yeah, that discontinuity is removable. Just define that value right there to be the value at c. That's removable. When they go like this, ain't no way you can define that away. That's non-removable. So a discontinuity at C is called removable when f can be made to be continuous by appropriately defining or redefining f of c to be that value of the whole loss. Then you're fine. Okay? And we'll see examples of that. Any questions so far? All right, here's some examples. For instance, the function shown here in 127a and c. Okay. What about this? Is this function continuous on the interval a to b, open interval a to b? No, because it's not defined at x equals c. Not continuous. Does it have a limit? At x equals c? Yes, it does. Whatever value that is right there. It does have a limit. For the left and right is the same. That would be it. So this has a limit. You can take that and say this function, whatever it is, this is what it is with that, and then make it as a piecewise defined function. It's this everywhere from a to b except at c, and it's that value at x equals c. Okay? Now you've removed the discontinuity by defining its value there to be whatever this is right there. Is this one removed? No. Okay. It's defined everywhere, defined from A to B. Doesn't have to be A or B. Defined here, it's defined here, defined everywhere past there, defined everywhere on there, but the limit here and the limit there are not the same. You can't remove that. Non-removable discontinuity. This one's defined everywhere, but f of c is not the limit as left and right limit as x approaches c. But you can redefine f of x at c, take it off of here, move it up there, and now it's continuous. So that's a removable discontinuity. You just redefine it. This one is removable because you define it in the first place. This one, there's no way you can ever make that connect. Ever. So it's not removable. Make sense? Okay. Big deal. Why? Okay. So let's talk about it. Discuss the continuity of each of these functions. F of x is equal to 1 over x. What you reckon, folks? Is it continuous? Everywhere? Say again? All right. Why not? Okay, x cannot be 0. The denominator can never be 0. So it's not continuous at 0. Number one, because it's not defined at 0. Is it removable? Can you give it a value to make it continuous at 0?
No.
Why not? Okay, think about what's happening at this. As x is getting closer and closer to 0 from the positive side, where is it going? Say x equal 1/2. 1 over x would be 2. X equal 1/3, it would be 3. X equal 1/10, it would be 10. X equal 1 over 1,000,000, it would be 1,000,000. Okay, it's getting huge. The closer it gets to 0, it's going this way. How about approaching 0 from the left-hand side? Like negative 1/2. Where is it now? 1 over x. It's negative 2, negative 3, negative 10, negative 1,000,000. You know, you're sitting in the classroom downstairs. Okay? Yeah. And no way you'll ever get those to meet. So that's it's not continuous, and that's probably all they're looking for, but we also can say it's not a removable discontinuity either. How about G? Is it continuous or not? It is continuous? What was wrong with it? A? You can't have 0 in the denominator. Oh, x equal 1, it's not defined either, is it? Because you can't divide it by 0 still. Not even going from A to B, you can't divide it by 0. But what can you do here? Say again? Factor. Okay, how would you factor that? X plus 1 times x minus 1, x minus 1, and then when you do that, you basically remove that discontinuity. And now you can plug in to what's here. See, that would have a hole at x equals 0, at x equals 1. But if you plug in x equals 1 here, that's going to give you hard math. 2, exactly. 1 plus 1 is 2. No, you'd be doing such high-level math today, did you? So your limit would be 2. So plug that value in. It's not defined. It's this value here. It's this function here. Everywhere x from negative infinity up to 1, not counting 1. And it's also that for every value from 1 to positive infinity, but not counting 1. So that's your piecewise defined function. But at x equal 1, define it to be 2. And now you filled in the hole. Now it's continuous. So it's discontinuous. B is not continuous, but it's a removable discontinuity. See? Okay? How about H? H is already piecewise defined. So probably have to do a graph with it. We love graphing, don't we? Kinda? Okay. So let's do a graph for this one. Okay? For x less than or equal to 0, h of x is x plus 1. So let's start with 0. When x is 0, what's your value? Okay, there it is right there. And then what would you tell me about x plus 1 to the left of 0 then? It's what? Not always. What is that a graph of? Yeah, and what is that? How would you describe that graph? Y-intercept is 1, that's why I put it there, good. And what? Slope of 1. Slope of 1, y-intercept of 1. It's a thing, and x-intercept would be 1, 0, right? Okay, that would work. So there it is. All right, now let's do the other one. H of x is x squared plus 1. Okay, this is for all x is greater than 0. But let's just guess. What would it be if x were equal to 0? Yeah. And what?
A parabola with its vertex, or what is it?
The vertex of what?
Vertex at 0?
At 0?
At 1.
At 1. So it would be a parabola that does like this. Okay? Yeah, okay, that's what I thought you meant. Okay? Now, that's a parabola. That's not a very smooth function at all. Okay? That has what we call a cusp at x equals 0. But guess what? It's continuous there. Because the value of this one is 1, and the value of this one at x equals 0 would have been 1 if it were defined there, right? Because you plug in a 0 here and you get a 1. And it picks up and goes from there. So yes, that's a continuous function. Don't have to do a thing to it. Not a smooth function, but continuous. How about y is equal sine x? Man, I gave that away, didn't I? What is it? Continuous everywhere. All right, very good. Any questions on that? Now, they're going to probably draw graphs on all of them, but let me clear out mine that I drew for this one. Yes, sorry.
So for G.
G, okay.
But if you plug into 0, the problem says equal to 1.
Okay, yeah. If you plug in x equals 0, yeah, it's 1. That wasn't the problem. X equals 1 is where the problem is. It's perfectly happy at x equals 0, x equals negative 15, x equals positive 10. Anything you want to put there, you're going to get a value. But you can't put in an x equals 1. That's the problem point. Okay. That's where the hole was. But if you plug in the hole with 2 at x equals 1, then you got it covered. Yeah. Yeah, it's not x equals 0, it's x equals 1 was your problem. So let's see what we got. Domain on the A of f is all non-zero real numbers. Okay, that was the 1 over x. Domain is all non-zero real numbers. Okay? All right. This is diamond, right? Okay, we're on page 75, example 1. We've already talked about them, now they're talking about it. 1a was f of x equal 1 over x. The main of that is all non-zero real numbers. Just can't count 0, okay? From theorem 1.3, somewhere back there, you can conclude that f is continuous at every value, x value in its domain. Yeah, okay, that's why it's in the domain, continuous there. But it says non-zero real numbers. The question is it continuous at x equals 0? And we know it's not. Oh, wait a minute. This is put together rather strangely, isn't it? Oh, 1.3 was somewhere back. Okay. Yeah, way back. Way back. Page 64 in section 1.3. Okay? Not that far back, but that's where it was. And they're just repeating it here. Sort of threw me. All polynomial functions continuous everywhere. No sweat there. But if R is a rational function, like that one was, 1 over x, okay, where you have the variable in the denominator given by R of x is equal to P of x, which in our case was 1, over Q of x, which in our case was x. And C is a real number such that Q of C is not equal to 0. It's defined everywhere, continuous everywhere, as long as Q of C is not 0. In other words, your denominator is not 0. But, so you're not worried about anywhere else. If when you plugged in x equals c, okay, to that rational function there, that would be P of c divided by Q of c. Well, here our x is equal to 0. That's our c, the place where it's not defined. Every c where it is defined, yeah, that's your rational function. But where c is not defined, like non-zero, x equals 0, then you can't plug it in at all. Okay? This is rather strange. It's just taking you back to the theorem that supports it. And this is what we're showing. To me, this is much better. X equals 0, F has a non-removable discontinuity. This is approaching positive infinity this way, negative infinity that way. Ain't no value you can plug in to make those meet at all. They're miles apart and getting further. Okay? Non-removable discontinuity X equals 0. Yeah, theorem 1.3, I guess, gives you justification for it, but yeah, that shows it. Okay, in other words, there is no way to define f of 0 so as to make it continuous at x equals 0. Can't do it. Infinitely far apart. No way you can connect it. Now, the B part, domain of G, is all real numbers except x equal 1. Remember, that's the one with x squared minus 1 over x minus 1. Not defined at x equal 1. Okay? But there we have a indeterminate form. In the previous one, 1 over x, that's not indeterminate. That's undefined, period. No way. So there's no way to connect them. This one, we don't know that for sure. It's indeterminate. Now, it could still be no limit, but we don't know that until we try. Okay? So what they're going to do here, from that theorem, you can conclude that G is continuous. Every x value in its domain, except x equal 1, it's just indeterminate at x equal 1. Okay? But if you plotted those, this is what it looks like. And that is that good old x plus 1 again that we just had in the other one. Okay? That we're going to have coming up. It's approaching 2 from this way. It's approaching 2 from that way. Yeah, if we plug in g of x is equal to 2 at x equal 1, then we've got it. We've plugged the hole, and now it's a continuous function. That is a removable discontinuity right there. Okay? By defining g of 1 as 2, you do a redefined function, which is that function for all values other than x equal 1, this function with x equal, this value with x equal 1, now it's a continuous function. So that is a removable discontinuity. This one, the domain of h is all real numbers. The function h is continuous from negative infinity to 0, and from 0 to positive infinity. Okay? But because the limit of h of x is 1 as you approach 0 from the left, or approach it from the right, it has the same limit. So this doesn't even, it's not even removable. It's continuous. The value for this one is 1 there. The value of this one doesn't start there, but if it did, it would be there. So it's not a smooth function. It's not smooth there, but it is continuous. Okay? So you don't have to do a thing to it. That is continuous everywhere. Make sense? No holes in that. Okay. Now this is still going back to 1.3, I'm thinking. See? Yeah. Oh yeah. This is the D one. And it told us that the limit that your sine and your cosine function were let C be a real number in the domain of the given trigonometric function, and this is true. Pretty really? Yeah, it works. The only thing is, for sine and cosine, that's for any value C will work. For the others, there are certain value C's where it won't work, where it's not in the domain. The domain of sine and cosine is all real numbers. So since it has a value of all real numbers, it's continuous to all real numbers. Tangent and cotangent, secant and cosecant, their domains are not defined everywhere. Tangent and secant are not defined at the half pies. Cosecant and cotangents are not defined at the whole pies. I like the sound of whole pies. So therefore, your sine function is continuous everywhere. Entire real number line. Negative infinity to positive infinity. Boy, they can beat something to death, can't they? Okay, let's move on to one-sided limits. Okay, this is top of page 76. And continuity on a closed interval. Okay? So, to understand continuity on a closed interval, you must first need to look at a different type of limit called a one-sided limit. Okay? For instance, the limit from the right, or the right-hand limit, that means you're coming from the right to the point C, means x is approaching C from values greater than C from the right-hand side coming towards C. That is defined this way. The limit is x approaching C with a plus up here, meaning approaching it from the positive side. Values greater than C. If that limit of f of x is equal to L, okay, that means this has a limit. Right-hand limit is x approaching C from the right. Okay? And if this is your C value, and here's your x, and the closer you get here, there is a limit. Whatever that value right there is, that's your limit. Okay? From the right. Limit is x approaching C from the right. Well, that function, same thing as it approaches C from the left. Same limit, so that's continuous at C. Okay? I'm jumping ahead, but it seems like they're dragging this out. Similarly, the limit from the left to the left-hand limit means that x approaches C from values less than C, approaching C from the left. Okay? So now the x's are coming closer to C that way, and there is a limit there too. And that limit was the same as when you're approaching from the right. Okay? So therefore, this function is continuous at C. But we haven't got there yet. The limit from the right is the same as the limit from the left. Then you have a continuous function. Okay, so one-sided limits are useful in taking limits of functions involving radicals. Okay? For instance, if n is an even integer, then the limit as x is approaching 0 from the right-hand side, n is an even integer, so it's a 2, 4, 6, 8, 10, 12, whatever. Okay, and when I would say even positive integer, because we don't put negative integers in there at all. So I would say even whole number. That would be a bit better to say. Even natural number would be even better. Okay, counting them. Okay, even positive integer here. Then the limit as x approaches 0 from the left. Yeah, you can take the nth root of 0. It's 0. Okay, you can do that. Okay, can you do it as x approaches 0 from the left-hand side? X can never be 0 if this is an even radical. Even index of the radical. You can't take the square root of negative 0.1, negative 0.0001. You can't take the square root of any negative number, no matter how small. So this is only good as you're approaching from the right. You can't do it from the left. Okay? So that's why it said useful for doing involving radicals. Now, if this would end with odd, no sweat at all. You can take the third root and the seventh root or the 13th root of any number, or positive or negative. It's only even roots you can't take. All right. So let's find find the limit as f of x approaches, f of x is equal to the square root of 4 minus x squared as x approaches negative 2 from the right-hand side. Okay? That means value is greater than negative 2. Any ideas? What you're trying to do is the limit as x approaches negative 2 from the positive side, from the right-hand side, of the square root of 4 minus x squared. What would you do? Plug it in, plug it in. What happens if you plug in a negative 2 here? That becomes a positive 2, 4, and 4, a positive 4, right? Oh, negative 2 squared is 4. 4 minus 4 is 0. Yeah, you can take the square root of 0. It's 0. If you approach negative 2 from the positive side. What if you approach negative 2 from the negative side? Okay? In other words, it's negative 2.1. So if you square it, negative 2.1, you get a positive 4 point something greater, right? 4 minus 4 point something is going to be negative. You can't do it. I can approach this from the right-hand side because, say, negative 1.9. Yeah. The difference there is a small but positive number. And even if it goes to negative 2, yes, that's fine. But go anything on this side of that, then this becomes larger than that. So this has a right-hand limit, but no left-hand limit. Okay? And that will be 0, by the way. Let's see what they do. Here is the graph of that. Now, how did they go about graphing that? Any ideas? So again, they just started plugging in x values? Yeah, you could do that. Here's another way to do it. What's f of x? Y. Okay? You could write that as y is equal to the square root of 4 minus x squared. Okay? Now the next step you do, you have to be very careful with. But what would be an obvious thing to do to try to get rid of that stinking radical? Square both sides. So we'll square this and square that. So that gives us y squared is equal to, and what happens when you square a square root? Radical disappears. 4 minus x squared. Okay? Right? Now, if I added x squared to both sides, you have x squared plus y squared is equal to 2. What's that a graph of? What function is that? It's not really a function. What does that describe? A circle of radius 2. X squared plus y squared equal r squared. How did I get a 2 there? You let me write a 2 there. Shame on you. Okay? That's a 4. Okay? I was doing 2 squared in my head and 4. And then write it as 2 squared. X squared plus y squared equal r squared, where r is 2. Yeah, that's a circle. But why did we only draw it this way? Because the circle is not a function. Why not? What does it fail? Vertical line test. You're only taking the positive square root of that, meaning your y's are always positive. That's principal square root. You don't see a minus sign of that. And it's defined here and defined here. So this is defined on the closed interval from negative 2 to 2. It doesn't have to be open anymore. It can be closed because the value is here and the value is here. And as x approaches negative 2 from the left-hand side, it's approaching 0. X not even defined from the right-hand side, so it can't approach from that side. It doesn't exist out there. You can't do it because then you would have a negative inside the radical. Okay? So that shows that as x approaches negative 2 from the left, from the right, from the positive side, this is approaching 0. It can't approach it from the left-hand side. The function's not defined. Okay? Make sense? Perfectly good function there. You only have to use the top half, but keep it a function. You could have put a minus sign in front of that radical, then you would have had the bottom half only of that circle. Okay. So one-sided limits can be used to investigate the behavior of step functions. What do you reckon those are? Step functions. It's like you're going upstairs or possibly downstairs. So they have some constant value on each interval, but they're discontinuous at the borders of those intervals. One of these, one common type, and boy, math books love this greatest integer functions. So far, I found very few real practical uses for them, but it's a good function. It looks kind of like an absolute value function, only you have a bracket on the outside. And what it means is the greatest integer n such that n is less than or equal to x. So give me an x, any x in the world. 5. What's the greatest integer in 5? Less than or equal to 5. Integer. 5. Give me another number, any x in the world. 2. Greatest integer in 2 is 2. Give me another x, any real value x in the world.
5 million.
Second?
5 million.
5 million. Greatest integer in 5 million is 5 million. Y'all like these whole numbers, don't you? Second? Negative 2. What's the greatest integer in negative 2? Negative 2. It's less than or equal to negative 2. It's equal to negative 2. That would be negative 2. Perfectly fine. You love your integers, don't you? Give me any other x. 8.75. Excellent. What's the greatest integer in less than or equal to 8.75? That's still not an integer. 8! 8! That's an integer. So 8.75 will be 8. 8 would be 8. 8.95 would be 8. 8.99999 would be 8. But 9 would be 9. It jumps up 1. It steps up 1 at the integral values. Okay? That's what the greatest integer is. Okay? Give me something on the other side. Well, negative 8.75. You like 8.75, obviously, right?
Yeah.
So what's the greatest integer in negative 8.75? Negative 9, because it has to be less than or equal to that. And negative 8 is greater than negative 8.75. So that would be negative 9. All right. So here's some examples. For instance, greatest integer in 2.5 is 2. In other words, drop the decimal, okay? If it's a mixed number, drop the fraction. If they're positive. But if they're negative, you have to always look to the left because it's less than or equal to. And the greatest integer less than or equal to negative 2.5 is negative 3. Always look to the left because it's less than or equal to. If it's equal to, you're on. Okay. But it's less than or equal to. Good deal. Make sense? All right. When the limit from the left is not equal to the limit from the right, which you've already been saying, then you can't stand up, sit down, fight. No, that's what you're okay. Then the two-sided limit does not exist. The next theorem makes this more explicit, as if it wasn't explicit enough. Let f of x, or f, be a function, and let c and l be any real numbers in the world. Okay? The limit of f of x as x approaches the c is L, is that value L. Now, remember, C is what X is going on the X-axis. L is what the F is approaching, okay? The limit of f of x as x approaches C is L, if and only if the limit as x approaches C from the left has to be L, and the limit as x approaches C from the right of f of x also must be L. They must be the same from both directions. If they're not, even if they're just a little bit off, limit can't exist. Okay? But if they are the same from both directions, even if it's not defined at x equals c, if f of c is not defined, if the limits exist there from the left and right, then the limit does exist, even if the function doesn't. And we saw that before. X squared over minus 1 over x minus 1. Limits existed from both directions, you can plug in a value. That's a removable discontinuity. So the concept of one-sided limit allows you to extend the definition of continuity to closed intervals. Okay? Basically, a function is continuous on a closed interval when it's continuous in the interior of the interval and exhibits one-sided continuity at both endpoints. Then you can say it's continuous in the closed interval. This is stated formally in this definition. Lots of definitions to that. Definition of a continuity on a closed interval. Function f is continuous on some closed interval a to b. Notice here, if you count the endpoints, you put square brackets. If it's an open interval, you put parentheses, meaning you don't necessarily need to be defined at a or b. Okay? When f is continuous on the open interval, so for it to be continuous on the closed interval, it's got to be continuous on the open interval. Okay? And that the limit as x approaches a, since this on the left-hand side, from the right is f of a. And the limit as x approaches b from the left-hand side, from the left, from the negative side of f of x is b, then it's continuous from the left and the right at those endpoints. Left from the right at a, from the left at b, then it's continuous on the closed interval a to b. Okay. If this had a dot here and a dot there and it's continuous at both dots, that's continuous on the closed interval. If that was an open circle there, you can't say. It would only be on an open interval, a to b. But if it's a closed dot, you're okay. That's why that square root of 4 minus x squared, those dots were on both ends, so that it was on the closed interval. Okay. So let's discuss the continuity of f of x equal the square root of 1 minus x squared. Is that continuous everywhere? Yay or nay? No. Now, here's kind of how to do this mathematically in a little bit of a complete way, I guess you would say. When you see this in a radical, and the radical has an even index. Now, if you don't see an index on a radical, what do you assume it is? 2. That's the only time. If you don't see a coefficient, assume it's 1. You don't see an exponent, assume it's 1. If you don't see an index on a radical, assume it's 2. It's a square root. That's what we call it, square root. Okay? This is even, so the thing under here, 1 minus x squared, has to be what? Okay, how do we write that mathematically? If something is positive, it's greater than 0. But it doesn't just have to be positive, it could be 0 itself. So it's greater than or equal to 0. Right? Okay? Now what can we do with that inequality? Solving for x. How would you go about doing that? There's a couple techniques you could use. Subtract 1 from both sides was certainly a legal thing to do in most states. Okay? So that would be, that goes to 0. This will be minus x squared is greater than or equal to negative 1. Okay? Divide by negative 1. Okay, and what do you do then? X squared, 1. What do you do with the symbol? You flip it. Anytime you multiply or divide by a negative number with a directional inequality, that's less than or equal to, greater than or equal to, less than or greater than. The not equal to, you don't worry with. But the inequalities that have a direction to them, If you multiply or divide by a negative number, you have to flip the direction of the inequality. So this says that x squared has to be less than or equal to 1. So what x's could you put in there? Second? Okay, is negative 3 less than 1? Okay, so you put negative 3 in there? Negative 3 squared is? Is that less than or equal to 1? What's it got to be? Okay. No. What would a negative 1 do for you? That would be fine. That would be perfectly fine. Negative 1/2 would be perfectly fine. So what would x have to be? Yeah, okay. Getting close. Got it. Between 1 and negative 1, counting it. So your interval here is -1 less than or equal to x less than or equal to 1. The absolute value of x has to be less than or equal to 1. So that is your interval. That's the closed interval. That's where it's defined. It's continuous everywhere on that interval, not even defined outside the interval. Okay? And that's a closed interval. It's even continuous at the endpoints, but not anywhere else, because it's not even defined anywhere else. Okay? Now that's how I do it. Let's see how they do it. They may do it slightly differently. Let's see. The domain, domain of alpha is the closed interval. That's what I was doing. I was finding the domain for you. And it has to be between -1 and 1, inclusive. It can include the -1 and 1. Now, what if this had been the Ln, or any log of open parentheses 1 minus x squared? Second? Yes, now you would have parentheses here. Exactly. Because you can't include 0 there. Square roots you can include 0. LNs you can't include 0. It's got to be greater than 1. It has to be positive there. So yeah. So sorry, that was a commercial break for David. Okay. All right. We're targeting him. Okay. So at all points on the open interval -1 to 1, continuity of alpha follows limits theorems 1.4 and 1.5, which we already did. Whoa, he loves to go back and recall his theorems. Okay, if n is a positive integer, the limit below is valid for all c when n is odd, and it's valid for all c greater than 0 when n is even. Okay, and I think when we did this one before, I said there's no reason not to do c is greater than or equal to 0, because that's still okay. Okay, so they're still writing it as if it has to be greater than. It could be greater than or equal, just like we saw here. Okay, and 1.5 was the limit of a composite function if alpha and g are functions such that the limit of, as x approaches c, of g of x is L, and the limit as x approaches L of alpha of x is alpha of L, then the limit as x approaches c of alpha g of x would be the limit of, f of the limit of x approaches c. It just, boy, remember, it's just a sort of a circular argument, but it's absolutely true. What they're saying is, now what they're saying on this one, and this is what I started with the inside and worked my way out, that's the same thing they're doing here. If you find what it is for g, that you have to have the g to be positive, and that's what we did. 1 minus x squared had to be greater than 0. Okay. So the limit of this is 0 as x approaches -1 from the left, as x approaches +1 from the, I'm sorry, I said it back, -1 from the right, +1 from the left, then both of those are zeros. This is continuous everywhere, because the function is defined everywhere, and this is why they include the endpoints here, because their theorem didn't include the endpoints. They valued the endpoints. Yes, that's true. So that this is a close. Seems sort of extra work to do it that way, but that's how they do it. Kind of makes sense. And again, this time your radius is 1. Before it was square root of 4 minus x squared, the radius was 2. Now the radius is 1. There it is. Circle just like before, only smaller. Make sense? All right. Whoa. All right. Again, this is the first time I've taught from this book, and I just got a little carried away, I think, because I skipped example 3. I wondered why they didn't have one. So let's go back and do example 3. Sorry about that. Let's find where it is. Well, yeah, we did 4, and I didn't even notice we had skipped 3. There was example 2. So let's clear this out of the way. Let's do example 3 here. Sorry about that. How we do it? Fine. Okay. Example 3. I knew they wanted to do one of these. It shocked me they didn't. Find the limit of the greatest integer function f of x equal f of x is equal to the greatest integer in x. That's probably not a very good looking symbol. As x approaches 0 from the left and from the right. Find the limit of that as x approaches 0 from the left-hand side and from the right-hand side. Okay. Well, what they did was draw the graph of the greatest integer function. Okay. Okay. Help me draw it. X equals 0, what's the value? 0. Okay. X equal 1. 1. X equal 2. 2. X equal 3. 3. X equal negative 1. Negative 1. Okay, we got those points done. Okay. Now, let's do something in between those points. Give me a value. 1.5. That would be over here. What's the value? Greatest integer in 1.5. 1. Okay, so it's there. Give me another one. Negative 1.5. That would be here. What's its value? Second? Negative 2. Okay, so it would be here. So here's what we got happening, folks. I'm just going to cut to the chase a little bit. This is 1 everywhere up to, but not at 2. At 2, it goes up to 2. Then it's at 2 everywhere except at 3. It's not at 3. It goes to 3. Then it goes up here, open there. Same thing here. This is good here, open there, good here, open there, good there, open there, good here, open here, and so on. That's what the greatest integer function looks like. Okay? It's a step function. You go on like steps as you go. Don't just step here because there's no back there. Now, it's defined everywhere. Nowhere where it's not defined is it continuous everywhere. No. Okay, where is it discontinuous? At the integral values. 1, 2, 3, 4, 5. 0, 1, 2, negative 1. Every integer you have a jump. So what is, it's asking for, what is the limit of f of x, well, let's not even write f of x anymore, limit of greatest integer in x, because that's what that is. Okay, the greatest integer in x as x approaches 0 from the left-hand side. What is that limit? X approaches 0 from the left-hand side. What seems to be the limit? Again? -1. You got it. Okay. And what's the limit of absolute value? Greatest integer in x as x approaches 0 again, but this time from the right-hand side. 0. Okay. Is that continuous at x equals 0? No, because it has a different limit as it comes from the left as it does from the right. Got it. Okay. Now, we already did example 4. Sorry, I got carried away. All right. And before we get to properties of discontinuity, okay, let's go on and let's do example 5. There was example 4. Let's do 5. Page 78. On the Kelvin scale, what are we talking about? Kelvin scale. Second? Not weight. Temperature. And the Kelvin scale has another name. Anyone know what it's called? It's called the absolute scale sometimes. Here's what we mean by that. On the Kelvin scale, you can never, ever, wait, let's start over. What scale do we usually use? Fahrenheit. Okay, now, doesn't happen much here in the South, but go up to Minneapolis. Can you ever get negative on the Fahrenheit scale? Yes, they do it fairly frequently in the wintertime, right? What's another scale? Celsius scale. Can you ever get negative on the Celsius scale? Even here in the South. Like a couple weeks ago, we were below freezing. That's negative on the Celsius scale. On the Kelvin scale, though, that's why it's called absolute scale, never, ever, ever have a negative number. In fact, the third law of thermodynamics says absolute 0, that means on the Kelvin scale, can be approached but never reached. So you can't even get to 0 on the Kelvin scale. In other words, 0 is as cold as you could ever go anywhere in the universe. You can't get any cold. You can't even get to 0 on the Kelvin scale. Okay? Now, something just, this is an aside here. On the Fahrenheit and Celsius scales, we use those little degree symbols. Kelvin scale never, ever use a degree symbol. It's 7K, 85K, 514K, negative 3K, right? You can't do it, right? You can't have a negative on the, and you can't ever get to 0. You can talk about 0K, but you can never reach it, okay? They say, I've read it somewhere in a physical science book, they've gotten within a few billionths of a degree of 0, but never at 0. How in the world do you measure a billionth of a degree Kelvin? I mean, a billionth of a K. And how do you know whether you're above or below? That beats me. Okay. I don't have any devices that can do that. But anyway. So let's do. That's what we're talking about. On the Kelvin scale, this is example 5. Absolute 0 is the temperature 0K. No degree symbol. 0K. I'm going to slash my 0 so you don't think I'm saying okay. Okay, although temperatures very close to 0K have been produced in laboratories, absolute 0 has never been attained. I was just saying that, third law of thermodynamics. In fact, evidence suggests that absolute zero cannot be attained. Okay? How do scientists determine that 0K is the lower limit of the temperature of matter? And what is absolute zero on the Celsius scale? Okay? There's really not a lot to do here, but we're going to do it. The determination of absolute zero stems from the work of a French physicist, Jacques Charles. I like his last name, don't you? Okay. And by the way, you'll see this if you do any physics or physical science. Charles's law. He came up with a few laws too, but that's not his first name. That's his last name. Charles discovered, that's last name Charles, discovered that the volume of gas at constant pressure increases linearly with the temperature of the gas. Okay. So let's do some arm waving here. Sorry, folks, if you're at home, you won't see this. But if you had a scale here, okay, and you had a gas. Now, gases usually are relatively reasonable temperatures, right? So a gas at some temperature, and here's its volume. So volume is here, temperature is here. You increase the volume of the gas, and what does it do? Expand. So you got something going up here. So what happens if you start decreasing the temperature of the gas? It gets smaller. Okay, the volume decreases. And it continues to decrease, and continues to decrease, and continues to decrease. What happens to any gas when you get cold enough?
It freezes?
Second?
It freezes or turns?
Well, actually, it first goes to liquid, or it could go to a solid. In other words, you know, it collapses because it's no longer a gas. So somewhere down here, it is going to a liquid, and then it just falls off. So you can't still do it. But he did this for this gas. He did it for another gas. He did it for a bunch of different gases, and they may have different slopes and everything else. But guess what? He found all those lines, if you extrapolated them and drew them, they were heading down here. And that was absolute zero. Now, what would that mean? At absolute zero, the volume would go to zero. But if you have molecules there, how can you have a volume of zero? So theoretically, you can't ever get to absolute zero, but you can't get to a volume of zero. Okay. Now that's not what they use these days. That was original. Now they do it in quantum mechanics. If you understand quantum mechanics, that's another story. Okay. So anyway, he discovered the volume of gas at constant pressure increases linearly with the temperature of the gas. The table that's below here illustrates that this relationship between volume and temperature. To generate the values on the table, 1 mole of hydrogen is held at constant pressure of 1 atmosphere. The volume V is approximated and measured in liters, and the temperature T is measured in degrees Celsius. Degrees Celsius. Okay, you can get negative there, well, okay? And these show the things. Now, I'm not going to plot these, but if you got your books, look at them. And it goes down to minus 40 Celsius, and it goes up to plus 80 Celsius, okay? The points on the graph, yuck, okay? For those who don't have the book, I'll show you what this is looking like here. Ooh. Okay. Here are the points here, from 80 up here to minus 40, somewhere down here. Those are the points. And look at that nice straight line, okay? And if you continue dropping the temperature, and this is hydrogen gas, it does keep reducing, but then when you get something like, I can't remember for sure, it seems like it's within a few degrees, 4 degrees or something like that, of absolute zero. It then either drops out to be a liquid or a solid, one or the other. It either condenses or it freezes, one or the other. At some point, but it's awfully, awfully cold. But if you extended it there, you'll see it's getting close to, it doesn't get quite to negative 300 Celsius, it got to something like negative, okay. So here's what we're going to do. I don't know, this almost seems like it's, okay. They gave you the points on the table, and then you could use those points to come up with a formula, okay? And it's not, I mean, it's a straight line. You know how to do that. Change of y over change of x. Your y here is your volume, and your x is your temperature. So if you did the change of y here, the volume, so the slope is delta V over delta T. T being temperature, okay? V being volume. So let's do this as 80. That's the maximum you have. I'm sorry, that's that's your temperature. Okay. Your maximum volume in that table was 229.0038, and that was at 80 degrees Celsius, minus your minimum was 19.1482. 19.1482. That's just any 2 points on the graph, and that was at a minus 40. Okay, so this will be, I'm going to need some help with my math here, 9.855.6, I think it is. And this will be 120 down here. 80 minus a minus 40 would be 120. So someone with a calculator do 9.8556 divided by 120 and see what you get. Okay, say that again. 0.08. Say again. 213. That's what they got in the book. Good for them. Okay. So that would be your slope. So then you could say volume is equal to 0.08213 T. Okay. Yeah. Now, you need to put in a y-intercept. Okay. So that's what goes next. The y-intercept here for this gas, hydrogen gas, seems to be somewhere around 20. Oh, there it is. When you plugged in a zero, well, when you had a zero, it was 22.4334 from your table, right there. When y was zero, I mean your x was zero, that your t was zero, your v was 22.4334. So there's your y-intercept, plus 22.4334. Now this is their experimental results. I guess Charles did it or whoever did it. There's your formula. Okay? So what you can do now is, what happens is that as your t approaches zero from the left-hand side, I mean from the right-hand side. Well, let's solve this for t. And that would then be V minus 22.4334 divided by 0.028213. This would be what T would be. Okay. Subtract from both sides, divide by that. Okay. And that's what you're trying to take the limit of. The limit as the V is approaching zero. Your volume is approaching zero from the positive side. It can never be negative, okay, from the negative side of this thing right here, of this thing here, V minus 22.4334 over 0.08, I can't write, 213, okay? Well, let V go to zero. Put a zero in there. So all you do is take negative 22.4334 divide it by 0.08213. Divide those two numbers. What do you get? 22.4334 divided by 0.08213. Okay. A little louder. Negative 273. 14. Okay, that's enough digits. Okay. Now, what we usually say, rounding that to 4 digit, is approximately negative 273.15. Okay. That in degrees Celsius is equivalent to 0 K. Absolute 0. Okay. So that's how we get that. Now, a lot of times we'll say negative 273. And that's close enough for government work, but it's really negative 273.15. But then how good are your measurements anyway? I don't know. So that's usually what you see in physics books is negative 273. So absolute 0 on the Kelvin scale is approximately negative 273.15 on the Celsius scale.
So let's say that nothing in the universe is colder.
Nothing in the universe can even reach that temperature. It can get close. And when they say a few billionths of a degree, you'd have to carry this, Yeah, I don't know what they're going to do that. Okay. It may be a few millionths. I don't know. That would be 100,000ths there. Okay. How do you measure that precisely? Beats me. Okay. They do the same thing for Fahrenheit, and the scale that's absolute 0 there is sometimes called the Rankine scale, R-A-N-K-I-N, I believe it is. No one ever uses that I know of. So anyway, I wouldn't worry with it. Okay. That was example 5. Not sure it was worth the time, but we did it. And you learned what absolute 0 was on the Celsius scale. On the Fahrenheit scale, it's what, negative 4 to 59 or something along in there. Okay. So, well, I didn't need to do that. I could have just paced through. All right, let's now look at properties of continuity. Oh, man. You can't tell me, can you? Yuck. I did waste too much time on that. So, we'll start here, properties of continuity, next time. Homework exercises here. You can do any of the odds, 5 through 9. All those are on calcchat.com. Number 5 is on CalcView. Any of the odds, 11 through 29. All those are on calcchat.com. 11 is on CalcView. Do either 31 or 33 or both. Both of them are on CalcChat. 31's on CalcView. Any of the odds, either 35 or 37, both are on CalcChat. 35's on CalcView. Any of the odds 39 to 57, all those odds are on CalcChat, but 47's on CalcView. Any of the odds 59 through 60, or through 63, those 3 are on CalcChat, 61's on CalcView. Any of the odds 65 to 69, they're all on CalcChat, 67's on CalcView. Any of the odds 71 to 70, no, either 71 or 73, they're on CalcChat. Neither of those are on CalcView. And let's see, wanted to make sure I'm not getting. Let's stop there. We'll pick up the rest of those next time. Okay? Good deal. All right, we've got 1.4 to finish, 1.5. We'll probably try to go through that fairly quickly because I think I'm taking too much time. As soon as we finish 1.5, I'll give you your first test. And remember, I think for some reason y'all want a take-home test, so I guess I'll give it to you. Okay? Good deal. Any questions? All right. going to shut this down and let it begin loading.